Hi there, this is Matt Heffernan, and welcome back to my channel. If you haven't seen the last couple episodes, I've been doing this little 8-bit battle royale between different classic 8-bit microcomputers and some of the newer versions of these computers. And in round one, we were doing the same basic program. Actually in the basic language that's native to all of these different computers, or at least readily available, and using more or less the same code, just having to be slightly modified to deal with some of the graphical differences between them, being able to generate a Mandelbrot Set fractal in the most brute force method possible, just using the Wikipedia-derived algorithm for it. And the point was not to make it super efficient, but to just test how these different computers go through doing the same sort of mathematical operations. And that was not just a test of those computers' different just computational capabilities, but also how the basics are written for them and how well suited they are to those particular platforms and take advantage and maximize their power. And what we're going to do now is actually go and rewrite this algorithm in assembly language and try it out on the original platforms that we did. But as a recap, the way that the end of the complete first round went, of course, the Commodore X16, not surprising, was at the leader of the pack, even with the emulated version of the Sinclair ZX Spectrum Next, which I had calculated at 34 seconds. That may be actually a little faster than it could really do it. There's a lot of controversy regarding how this basic program would actually be executed by the Spectrum Next, that is. So that's something that we would definitely have to see on a real system. But what we do want to get to are those original three systems. So because we saw here at the end of round one that among the classic systems, the BBC Micro and the Amstrad CPC are both at the top, very close to each other. And they also have a 6502 and a Z80 CPU, respectively, as do our original competitors, the Commodore 64 with the 6502 compatible 6510 processor, and of course the Spectrum also has a Z80. But what I don't have really working at this point is a tool chain for getting programs, assembly programs, to work on the BBC or the Amstrad. So we're focusing right now on the stuff that I can do right this moment. And we're going to see how much faster it is to be able to run these programs by writing it right in assembly. So we'll take first a look at that Commodore X16 code, see how we get that into assembly. And of course, that assembly code is going to be very similar to what we do for the Commodore 64. And then, of course, we have to sort of rethink the whole thing for translating it for the Spectrum. So let's get right to what we have. So over here in the text editor, as a bit of a recap, here was the original basic program as it ran on the Commodore X16. And on all these other platforms, it was pretty much the same. What we're doing is we're doing 22 columns, or rather 22 rows and 32 columns, because that's the capability that we have with the ZX Spectrum. And so we use that as our lowest common denominator. Now, some of the other micros on the list did not have the same kind of color capability, where you had 15 unique colors. But we're still sticking with that baseline for this test. And by saying, okay, we're going to do up to 15 iterations of the calculations to generate the Mandelbrot set. And so here we can see in this in the Commodore X16 code, we are going through and doing VPokes and using the XY coordinates here in PY and PX, and calculating where in VRAM we want to poke this iteration count. So how many iterations we went through. It's after we decrement by 1, it's going to be somewhere between 0 and 14. And then we multiply that value by 16 so that we get the upper nibble set. And that to that color, which will be the background color. And then the foreground color will be immaterial, because at the very top we did a screen 0, which clears out all the foreground. So makes it very simple, but we can't just do exactly this necessarily with assembly language. So there's definitely a different approach for doing some of these things. But the good news is, of course, all of these approaches are generally going to be faster than the way it works in BASIC. So first, let's take a look at really the hardest thing to do, which is all of this math. Like we can see here, we're doing multiplications and divisions, and with this BASIC, we're doing them as floating point. So it's not just integer math that we're having to do here. And not just integer math, but on top of that, multiplication and division, which we don't have native support even for integers on either of these processors. So to do that, it means we're going to need to sort of rule our own. So what you can see here is I've created when I do the assembly language for this Commodore X16 generation. I have a lot of the standard stuff up front. I'm doing these defines right here. And instead of screen 0, I do this. I just up by 2 scale. And that will get me where I need to be. So it gets that 320 by 240, the 40 column mode effectively. So it's just really just zooming into that upper left corner. And then I do a loop, and I'm using the X register for the X value and the Y register for the Y value. And then I call this this method called mandget. And what mandget is, basically you pass an X and a Y value to it, and then in A, it'll spit out what that I value is. So like basically it does all of this, rather all of this, and then gives me the I that comes out, and I pass in an X and a Y value going in. So real simple. Oh, let me get back here to the code. So let's see what happens after that. Then, because this is the Commodore X16, I've got to use the Vera registers for actually doing this poke. But where am I poking it to? Well, I've got to calculate that address, because as we can see here in BASIC, I'm doing this multiplying by 256 for the Y, multiplying by 2 for the X, and then adding one more. So I'm going into the color for the character that I'm dealing with, and not actually changing the character code. Well, I'm not. I still, what I'm going to have to do in assembly is I still need to actually put those spaces in there, because unlike the basic screen command, I'm not clearing anything out. So I'm going to have to go write that space and then write the color value for that space character. So to do that, I need to set up my Vera Bank address, and that's going to be a stride of 1, but bank 0, because we're starting at the very top. Y is going to be, by virtue of the way VRAM is structured, whatever your Y coordinate is, that's going to be the upper nibble of the Vera address. So, just like we saw before, multiplying by 256. Of course, that makes it super easy. But then we still got to multiply X by 2. So there we have to bring X into the accumulator and do an arithmetic shift left and that will effectively do our multiply by 2. Still, we're dealing with integer math, integer multiplication by powers of 2, or in this case, by powers of 256, where I just got to put it in a different byte. All makes it very simple. And so then, once I have that, that complete address already in the Vera address registers, now I can just start poking the data in by storing it into the data port 0. So I'm getting the space character, which of course is hex 20. It's ASCII, PETSCII, same difference. 20 hex is our space. And we're storing that in data port 0. So now we've got a space there. It'll clear out any characters that were there. Then here, you see I do this pull A because I did a PHA here, which was pushing the value of I, the number of iterations, to the stack. I'm getting that back off the stack, and just like in the basic, I have to multiply that by 16, get it in the upper nibble. Of course, in assembly, that means just doing 4 arithmetic shifts to the left. And then we're storing that color value right after the character screen code, and we're done. So that's the whole iteration, and then we increment x, see if we're up to the width yet. If we're not up to the width yet, we go back to the top of the loop and do the next calculation. Once we do get up to the top of the width, we're resetting x to 0 and then incrementing y and doing the next row of squares. And we keep doing all of that until y gets up to the height, and then we no longer take this branch to go again back to the top of the loop. Then at the end, I just do all of this. I don't want the ready prompt to be in the middle, so I want to call plot. But in order to say I want to move a character to a certain place, I got to clear the carry bit. I am taking the y, and I want to make that into x because I want that number of rows that I've just rendered to be in x, because the kernel plot function has x and y swapped. It wants you to put the y coordinate in x and the x coordinate in y. So I take that y coordinate, move it over to x, but for the x coordinate, I want it right at 0. I want it right at the beginning of the line. So I load up y with 0. I call the plot kernel function, and we're done. So the question is, how much faster is that? It took us 23 seconds to do that in BASIC. But now I can load up this man.prg, which is what I've built this assembly language file to. And now we're going to run it and see how long it takes. I got my stopwatch ready, and we're going to hit them both at the same time. And go. Yeah, so about 3.5 seconds. So not too bad. A lot faster than 23 seconds. And so now we can get a good idea of just how much more efficient this assembly language approach is to our basic approach. Now, why is that? Why is it so much faster? Almost by a factor of 10. Well, of course, that is because of the floating point interpretation. So not just interpreting every line, but then interpreting every single numerical value as a floating point. And in this case, we're dealing with something where we have known bounds. We don't really need to use floating point. We can do fixed point. And through going through this algorithm and looking at the internal values it creates, I determined that we can just do the simplest possible 16-point fixed point value by having the upper byte be the integer value, and that can be assigned integer, and then the fraction would be in the lower byte. So effectively, we are just taking the integer value, the 16-bit integer value, and effectively interpreting that as being divided by 256. So if you did have 256, that is 1 in the high byte, 0 in the low byte, that would effectively be 1.0. And that's how this fixed point library is going to work. So it makes the code very fast. We're not having to do a whole lot of fancy stuff. And what I was able to do was reuse a fixed point library I had created before. That library had used a 9-bit integer and then a 7-bit fraction, so it was a little more complicated, but not too bad here. So the way that I do that is by creating these virtual registers. So we can see here, it's all on the 0 page. So for the Commander X16, I determined that hex 28 on the 0 page is going to be their floating point A register. And then we have a B register and then a C register. So generally the A and B registers are going to be the operands, and the C is going to be the result of an operation. And then we also need an additional register that we're calling R, because the most common use case for it will be as a remainder for a division. So how do we actually use these? Well, what I've created with this library, like I did before for this earlier line demo, which you can find on my channel. Look for the wireframe demo, sort of the first part. I never really advanced beyond that, but I did create this fixed point library to do that. And that allows me to just do all sorts of basic 2D geometry math using this fixed point library. And so it still keeps it very much in the sense of assembly language, dealing with registers here. So what you can see here is I am calling this function fp LDA byte, which loads whatever's in the accumulator into this A register on the 0 page. And then we also have this macro fp LDB to load B with a value that's in memory, this m and x max, which we can see here is this fixed constant value of 380 hex, which is effectively the same as 3.5. So we got 3 for the upper nibble, and the lower nibble is 80, which of course is halfway from 0 to 256. So that's how we get 3.5, 380. Simple enough, right? So that's what we do. We put in our x coordinate in A, because x is coming in when we call mand get, and we get the x value in A, and then we get B, and then we multiply. We get A times B by calling an fp multiply function, and what this function will do is put the product of A and B into C, and then we can transfer C to the A register, and then we are loading up the width into the B register this time, and now we are going to divide do a divide B out of A, right? A divided by B goes into C, and what that will give us is this x times x max. It will be in B, or rather in A, and then the width will be in B. So we're dividing that maximum value by B, just like as we do before, and going through these steps of doing all of this until eventually we get what we're actually looking for. Again, on this first line is xz, x0 to be px times 3.5 divided by 32 minus 2.5. And that's what we'll see here is we're going to get x0. It's going to be that final addition, and that will give us this m and x0, which will be in C after the add. So add and divide, also add, subtract, divide, multiply, all different functions in there. And then we can store a value in C to a memory location. And effectively we do that. We go through the whole Mandelbrot set algorithm, and eventually, of course, we're storing X and Y on the stack so they can come back. And then in A, we are putting this the actual iteration count, which will end up in X here at the end of our loop. And if we are the Commander X16, we have the 65CO2. So we can just transfer that right to the A register and then pull Y and X right off the stack with PLY and PLX. We don't have these two instructions for earlier 6502s, so we got to do it the hard way by storing it to a temporary value, then pulling the Y value off the stack. So we got to pull into A first, then transfer it to Y, and then we're going to need the X value, which we got to pull into A, and then we can transfer to X, and then we can get that value he had stored in the temporary variable back into A, and we're ready to return. So that's how we deal with some of the differences in different 6502 model numbers. And we can reuse this entire code for the Commodore 64. Not too shabby. So we'll take a quick look here now at how this is implemented. So we saw here we have the LDA byte, where we're just loading a byte that is in the A register into the lower byte. So we're storing that in, or not in storing in the upper byte. We're storing it in the upper byte because that's going to be an integer value. So we're assuming whatever's in A is an integer value, and we put that in that upper byte, and then the lower byte, we just say, well, it's going to be 0.0, so we just store 0 in the lower one. And again, where we have a different thing where we can do store 0 if it's 65CO2. If not, we got to do the whole load A with 0 and then store it. And so, yeah, so we're dealing with all that. We do the same thing for B. If we're loading from 2 full bytes from an address, then we are going to use this macro where we are loading that address into FPA or FPB. So doing the 2 bytes there. And then for C, generally we are storing the C. We're not loading anything into C. So we just sort of do the opposite, where we load what's into C and store it at that address. Very simple. And then we have floor functions, which we don't really use for Mandelbrot Set. And we have the transfer macros we saw before. We go from C to A or C to B, and then subtract. Now, the nice thing about this type of fixed point is that we are effectively just a factor of 256. We can still just do a standard integer add or subtract, and it will still work. So you can see here, it's the standard 6502 subtraction, where we got to set the carry bit and do the SBC on the lower byte and then the upper byte. And then same thing with add, where we got to clear the carry bit and then do an add on the lower byte and then an add on the upper byte. Just same way you would do it for a 16-bit integer. And it works the same way. It's transparent in this fixed point orientation. Divide, it's a lot more complicated. I'm not going into the details of it, but I invite you to go to the repo. It's linked in the description, and you can see how I go through this whole divide process with a fixed point value. But ultimately, it works. It takes care of all the different sign things you can do and making sure that you don't divide by 0 and all that other fun stuff. And then multiply, it's a similar thing where we are doing that multiplication and addressing the integer value and the fraction, and eventually getting everything all worked out. So you can look through that. I don't have a ton of explanation. You see, I don't have a whole lot of comments in this code, but these are based on standard algorithms that you can find that are out there. Just for basically doing 16-bit fixed point or just any sort of fixed point on a 8-bit processor. So that's how we get it, and that's how we get so much faster, because we're not doing these much larger floating point values, it's a lot more complicated to do that math. This is keeping the math mostly in the realm of integer math. We're just kind of shifting things around a little bit. So it just has only a slightly more complicated than doing integer math. So not too bad. So now what does that mean for our friend, the Commodore 64? So for the Commodore 64, we have a different Mandelbrot.asm. And so we don't have the VIR to deal with. We're just dealing with the memory map of the Commodore 64. So the first attempt I did at this, it was doing the exact same thing that the assembly language one did, or rather the basic one did, which was to do the pokes, into different parts of RAM based on calculated addresses. And so we can see here we're doing the same thing, although here we are using care out to print the clear screen character so that we can just do like we did before, where we are doing that that print. And here we can actually use the hex value instead of the decimal value, which makes it a little easier. But then otherwise, we're doing the same thing where we're doing this get function, and the I is going to be coming out of the A register, and we store that in this temporary I result. But then what we have to do is convert the X and Y value into the memory address that we need to set the color in, and to set the background color in. And, or actually, I'm sorry, no, it's the foreground color for the Commodore 64. We're going to set the foreground color and place the that reverse space there. And so, yeah, it's all pretty simple. We just have to get like the Y value and multiply it by 40. And of course, to do that, that means we have to shift it 3 times, and shifting it 3 times, and then putting it into floating point B, and that will give us y to the 8. And then we can do while we just have that stored in floating point B, back in floating point A, we shift that y value 2 more bits, and that will give us y times 32. So then we just have to add them together. And that's what we do. And what we get is then added in A, FPA, we have that y times 40. And then we just add in the X value by bringing X into A, and then adding that to that y times 40 value, and storing that in there. And then we're also storing that temporary value in B of y times 40 plus X. And then we got to bring in the screen map. So the screen map is at hex 400. And so we need to add this y times 40 plus X to the screen map address, which we do. And we keep that in FPA. And then since FPA is on the 0 page, we can then use that with our indirect mode, and the indexed indirect mode, rather. And we can put this reverse space character in there, and not just at that address, but also at later addresses in there. And so it all works out. We can do by setting X to 0, then we can just do an indirect like that. And then we do the same thing with FPB, where we had that original y times 40 plus X, and then we need to add in the color map address, which is D800, but we're adding that same offset in there, and then we're storing that into FP1, and then loading into A the result that we want, that color index. And here it can just be the color value from 0 to 15. And as you notice here, we don't need any sort of array there. We can just put that color index value from 0 to 14 right in the color map, and we're good to go. And then we're doing all the rest of the loop pretty much the same way as before, and even doing that same plot that we did at the end of the Commander X16 one, because again, we're dealing with a mostly the same kernel there. So what does this actually look like? Well, we load up man.prg. Whoops. Of course, out of device 8. All right, and then we'll run it. First, let's get our stopwatch ready and go. So definitely slower than the Commander X16 still, but a lot faster than the Commodore was before, where it was taking over 3 minutes. And here we can see I am about 13 seconds in or so. You're about halfway through. So where are we going to end up here? Getting close, and there. 26.5 seconds. Not too bad, right? Remember the basic program running on the Commander X16 did it in 23 seconds. So here you're getting that 9 times performance boost just by switching to assembly language. Now, as we saw here, that the assembly language, since you're using a 6510, you don't have some of the new time-saving and space-saving features of the 65CO2. So it's understandable that it doesn't quite match up with the same sort of performance boost that we get with the Commander X16. It is a different program after all. So, but here's the thing, is that this is very complicated because what we were doing is, we had to do sort of random pokes in there because we couldn't just use print to print those characters into the console, because every time you do a print, it does it on a new line. Well, in assembly, we don't have that problem. If we're using care out, it doesn't do an enter into care out until you've actually hit the enter key. So, well, let's take advantage of that. So I made a much simpler version of this here that now it has to just use care out for doing all of the graphics. And so we can change the color, we can print characters, we can return to the next line. We can do all of that stuff entirely with care out calls. Very simple. So first I need to get the actual control codes for switching these colors. Instead of the 0 through 14, I got to use these values. And they're kind of random in there. And I did a different order too, because trying to reorder these into the order of the original palette, the indexed palette, it was too much. And this way I could make black last. So it looks more like a regular Mandelbrot set. And then here I do the same thing at the beginning. I do a clear screen, and then I do a reverse on, and I start after I get the result of that Mandelbrot calculation. I then I keep X on the stack. I've got that result in there. I've stored it into this temporary value, and then I load it into X, and then I use that to index into the color codes array. And now I've got that in there, and I can just print out that color code And it will actually change the color of the foreground of the next character I do with care out. And I'm going to do a space. And that's real simple. So now I've printed out reverse space because I did a reverse on before that. And then I do care out, and I just keep doing that for the rest of the loop until I get to the width where I need to do a return. Now, a return will effectively cancel the reverse on, so I got to do a new reverse on. And do that then for the next row. And I keep going where I just keep incrementing y, but I don't have to do any calculation with the coordinates because care out is handling it. The console interface and the kernel is handling all of that for me. And then finally, once I get out of the loop, I can restore my light blue text with another magic code, 9A, and do that care out, and we're back to where we started. So the question is, it was 26.5 seconds to do it with the other method, where I'm calculating poke locations. Now, you can do the calculations a bit differently while using this console application. It's not generally as fast as doing a bunch of pokes at random spots, but when you're doing it in sequential spots, like we are doing here, we don't have to calculate it each time like we do in the other method. We just let that running tally work to our advantage. So how's it going to shake out? Is this going to be faster or slower? Well, good news is if I go back in device, I'll load man2.prg from device 8. And we'll run that. So let's get our stopwatch ready and go. All right, so far looks about the same as the other method. So let's see, is it going to be any faster or slower? I think it does kind of look nicer because we are using this out of order color indexing. So yeah, it looks nice with the little black on the interior. All right, we're coming towards the end, and 26.84. So it takes just like a quarter of a second longer to do this. So that's how inefficient the kernel methods are. Even though you have that running tally of where you're going to poke next, all of the window dressing for these kernel methods still take up a significant amount of time, where you could actually just go in and calculate where you want to poke each time, and it's going to be faster than the kernel. Can't help you there. So that's really what you got to do, is if it's worth the time that it takes to calculate these positions and to just poke these values right into memory. And by not having to do a basic poke, by being able to do just assembly, loads, and stores, makes it very fast, very efficient. So here's the question now, 26.5 seconds. Much better than its time, but it was also better in basic compared to the Spectrum. So how's that going to work out? Is the Spectrum still going to lag behind? Well, what we need to do is have the same sort of thing on the Spectrum. Let me show you here what this looks like. I'll go into our Z80 view for the syntax. So what we're going to do for the Spectrum version is, again, we need to have an array for the color codes. And of course, that's very easy to do in assembly. In fact, a lot more efficient to do in assembly. And then we're going to do the same kind of things that we did in the other one, where we're going to do something to clear the screen. Here we're going to call the CLS basic function right out of the ROM. And then we're going to initialize x and y to 0. Here we're going to use b and c for x and y. So we can just do a single load bc with 0, and it gets both those bytes zeroed out in one instruction. And then we call another mandget function, And then we need to calculate where we're going to be poking this background color. So what we have in BC, of course, is X and Y. So we're going to take that Y value. We're going to put that into the low byte of HL, and we're going to start shifting that to the left. And we shift it 5 bits to the left, we're going to get Y times 32. And that works out because we've got only 32 wide for the color map. Makes that really easy. Then what we do is load up the color map base address into DE, and then do the addition of DE into HL, and that will give us that color map plus Y times 32, which is what we used again for poking. And then we just need to add in X to that. So again, we are loading up DE. The high byte was 0, the low byte with B, which is the X coordinate, and adding that in, and now we actually have the color attribute address. So it's actually quite a bit simpler to calculate that color attribute address on the ZX Spectrum, just because we're already dealing with 32 character wide screen. So that is one advantage, I suppose, of having a lower resolution display, is that you can make it the next power of 2 for these convenience factors. So there we go. That's fine. Now what's it actually going to mean? So now we need to actually get our color codes. So here I'm going to use the IX register, and we're going to load up the color codes into that, and then at least the color code address to that. And then in A, we are going to have that index address, that the iteration count is still there. You notice in all this code, we never did anything with the A register. And that's kind of the nice thing also about the Z80, is that you can have a value in your accumulator and do a whole lot that doesn't affect the accumulator. And you don't have to worry about storing it on the stack or something for later. But here, now we're ready to finally put that into the E register, which has been getting a workout. And D still has 0 from up here. So now we can just add that offset to the color code index, and or we add that offset to the color code's address. So we're indexing into the array, and now we get that color code into the accumulator, where we can then load it into that color map address that we've already calculated in HL. And then we're good. And then the rest of it all shakes out the same way as the other programs. And at the end, we're not even worried about the prompt, because we know the prompt's going to end up at the bottom of the screen. And that's why we're only doing 22 rows, because the 23rd row is where that ready prompt is always going to end up. So we're heading that off at the pass. Now, to do all this, of course, that means we need to have that same mandget function implemented, which we have here. And here we're using, again, you notice this very similar sort of meta assembly language for doing that, where we have an A, B, and a C register in fixed point land, and we're just doing all of these macros and then these functions for multiplying and dividing. It's all going to be the same sort of thing. So here we can see, and you can look at it in more detail in the repo, is how we're dealing with this. Now, we don't have such a thing as a 0 page for the Z80. So to have something to be fast, we need to dedicate registers to these values. So we're saying that the fixed point A register is BC, the B register is DE, and then the C register is HL, because HL, of course, is the destination for a lot of 16-bit math anyway. So that makes it work out easily. And then we can use whatever byte, or 2 bytes rather, that are being pointed to by IX as the R register. So we can be a little more inefficient with R. Shouldn't be too bad. But then we can see here that we define the macros in pretty much the same way, except we can do these 16-bit operations a lot more easily with the Z80 assembly, where we can just do a single load for 16 bits. And although we do have to indicate when we are loading a value from a sort of an immediate value or a register versus loading from an indirect address, where we have to add the parentheses here to do indirect addressing. And then, of course, we have that store C, where we can give the destination, and whatever's in HL gets written off to that destination, and we're done. And so, of course, we have the floor methods that we're not using, and then we have our macros, more macros for TCA and TCB. We just do pairs of loads to move those. It's between registers, so it's very fast. We're not dealing with any memory access there. And we're doing our fixed point subtraction instead of a function here. We're doing it as a macro because it's so very simple that it's not even worth calling a function for. So here we just load whatever's in BC into HL. We OR A to clear the carry bit, and then we do our subtraction. And then for add, it's even simpler. We can just use the add instruction, where we don't have to worry about clearing the carry bit before, and it's all good. Real easy. And then here we have implementations of divide and multiply using the same algorithm that we did for 6502, but translated into doing those same operations. And you can do effectively all of those same operations in Z80. Now, there may be algorithms that are better tuned for the Z80, but I did not go to the trouble of looking any of those up. I had an algorithm that worked for this specific fixed point format, so I just re-implemented it in Z80 assembly. And so there we go. Let's actually see. This is going to generate both a snapshot, and it's going to generate a tape image. So we'll load that right up into Fuse. So here I can say I'll open up the tape, and then I can do a J to load, of course, because that makes sense, and a couple quotes, and that will actually start loading it up. So let me reset my stopwatch, and we'll go. And here it comes. Coming in pretty fast. Again, much, much faster than the basic. So the question is it going to beat the Commodore 64? Coming down the pike. And go. Indeed it does. In fact, gets it all the way down to 20.5 seconds. Not too shabby. So we can see here for sure that the ZX Spectrum, once you release yourself from the shackles of Sinclair Basic and are actually able to get down to the bare metal of that system, you can get a lot more performance out of it and start to take advantage of those 3.5 megahertz that you're pumping through there. But again, it's not 3.5 times faster than a 1 megahertz 6510, because again, we're dealing with a lot more cycles for doing the same sort of thing. So it mostly evens out, but today, for round 2, we're giving the edge to the Speccy. So hey, We're not bringing up the rear anymore. So what we're going to have to do in the next episode, the continuation of round 2, is get these programs working for at least the BBC Micro and the Amstrad CPC. I have programs written for those. I'm just trying to figure out a way to get those loaded into the emulators and be able to run them like I have with these others. It's just a bit of retooling that I'll have to do, and hopefully that will be ready to go next week, and we'll have our completion of round 2. I'm probably not going to try the Atari or the Apple anymore. I know, I'm sorry. And again, I always welcome folks to try this stuff on the Spectrum Next, especially on the real hardware. This particular program should run just fine on the Spectrum Next. And if there are additional features within the Spectrum Next that you can do some of this fixed point calculation faster, I know that there's some support for 8-bit multiplication on there. That's not really going to help you with this 16-bit fixed point math, but if you know of some special tricks that are available just for the Next, by all means, throw me a pull request. If you have anything that's going to make these things work faster with the same algorithm I do, I'm not looking for a more efficient Mandelbrot Set algorithm, but if you have a more efficient fixed point math algorithm or a more efficient way of dealing with the graphics hardware of any of these systems, all of that is certainly up for grabs, and we can get these things a bit more tuned and execute this amount of math even faster. That would be really cool. So if you want to see when that's going to happen, you know what you got to do. You got to just subscribe to the channel. And if you haven't subscribed yet, what you waiting for? I know these folks here that you're going to see, they haven't waited. In fact, they've gone the extra mile, and they are helping directly support this channel and getting behind-the-scenes information and getting sneak previews of these videos before they come out to the general public. But, it's still free to just subscribe here on YouTube and click that bell so you'll be notified at the very moment that they become public. And come check out some of the other stuff, some of the stuff I've got back in the archives. You might be interested in some of that too. And we will be getting back to the Z80 tutorial series for the ZX Spectrum once this Battle Royale has a final and complete winner. And I think so far it's gone very well. It's very interesting, and I love seeing all of the comments out there, even some of the more trolling comments. You know what? The fact that you went out of your way to troll me for not having real hardware and claiming some things may not be, cycle accurate. Great. Show me, please. Take this code, run it on real hardware, and show me where the speed discrepancies are. I would love nothing more than to see that. All right? And of course, if you've got stuff you want to send me a Spectrum Next, you want to send me a Timex Sinclair 2068 or a Commodore 64, oh boy, would I love that. Please send that to me. I don't need to be dragged for not having this hardware. Having that hardware is expensive and it's difficult to maintain. And I'm just here for the programming. All right? Well, thanks all, and I will talk to you again soon. Bye-bye.